Welcome to ePathshala, postgraduate program in Masters in Architecture. In today's module, we will be looking at embodied energy. Now, what is embodied energy? That will be the first thing that we will be looking at. Measurements of embodied energy, materials and component data, and guidelines for minimizing embodied energy. Now, we have heard this term embodied energy several times in our practice. People have used it, but it's quite confusing as to what exactly is embodied energy. Now, embodied energy can be quantified, is quantified because most energy used in the production of building materials are finite and have emissions that are harmful to the environment. Now, these materials have low embodied energy, minimize emissions and waste of energy. Now, embodied energy is an upstream upfront process. Now, the way we will look at understanding embodied energy is simple ways. What is in a gist? It is basically means whatever material we are producing for construction or whatever we get to the construction site goes through a process. What is that process? For example, a steel. It would require extraction of iron ore, that would be mining, then processing, then it goes to the manufacturing plant, gets the extrusions done, then transport and product delivery. Now, this could be, if I give an example of the today's scenario, how this happens within India. For example, iron ores in Karnataka, that is the Bellary region, are extracted from mining. Their natural resources is shipped back to China. The manufacturing of the steel is carried out, and the same steel is transported back to India, and from there it goes to the wholesalers, the wholesaler buy to the retailers to the end construction site. That is a huge process. Now, imagine how much of energy has gone through this process. So, this to calculate that, this is what embodied energy is all about. It is the entire stream from upstream to the front end of the component. It's basically an entire life cycle analysis of the building till it reaches the building site. Embodied energy does not include, there are a lot of confusions within this, that embodied energy includes operational and disposable of building. It is wrong. It does not include operational or disposal of building energy. This would also be considered as a life cycle. This could be used in a life cycle analysis of the entire building material life, but it is not the embodied energy of the material. Embodied energy is just the upstream process till it reaches the site. That is the amount of energy from what we have spoken earlier is taken into the material, is extracted, and all the things is put together called embodied energy. But when it comes to operation and disposal of a building, that can be calculated separately and put into a one single holistic picture called life cycle approach, or life cycle analysis of that material. Now, lifetime. Now, the reason why we want to discuss about what would be the best, most efficient way. The longer the building lasts, the more efficient the building material is. Reason is, there is a huge amount of energy that goes into the building at the upfront. This you will see it in a few slides later, that how that variation happens, but there is upfront energy that goes into the material. But as it lasts longer, since as we mentioned earlier that operational and disposal is not part of embodied energy, it becomes more efficient. Okay. Building envelope elements are 1/3 of the construction cost and should at least last for 60 years to at least mitigate that energy which has gone into the building materials. The mechanical services motors are also 1/3 of the cost, but only last for 25 years. So, the amount of energy that goes in building the mechanical systems like your chillers, motors, pumps, pipes, and all those things, there is a huge amount of energy that is required for it, for like PVC pipes, iron pipes and everything. Now, this will last, these materials will last only for 25 years. So, which means that the amount of energy which you have put into it is not being able to mitigate or pay back the building that amount of energy. But when some materials like brick, stone, which use the least amount of embodied energy, are able to pay back the building, basically which means that it is able to pay back the environment. So, it is not as a much bigger impact. So, it is very important to understand the life. For simplicity, more complex forms, the more the material and labor required. So, embodied energy also depends on the way you design. We sometimes ignore this aspect in our design processes. It is very important that we take into this account. The more the complex the building is, the more the material is required, there is wastages and the labor also is required. So, which means that it will increase the embodied energy. For a simple example which I have given over here, A, B and C. A is just a rectangular box, perimeter 90 meter, 4 corners. When you look at the B, which is more on a horizontal, which is more stretched out rectangular, which has a perimeter of 500 square, it is the same square meter. All the three are of the same area, but the perimeter of the B increases almost by 30 meter, which means there is more material required in it. When you have a kind of a Z kind of a thing, then the perimeter also is the same as the linear one, but it has 8 corners, which means there will be more labor. So, it is very important that when you are designing it also, embodied energy or the materials which we use within a building should be taken into account, because this all has an impact on the embodied energy of the overall building. Important factors in reducing the impact of the embodied energy are to design buildings for long life. As I mentioned previously in the previous slide, that lifeline of any material is that it needs to, the building has to be for longer life. Durability and adaptability. When I say durability, it needs to be there for at least for certain amount of years. It cannot just disintegrate into a smaller. What I basically previously mentioned, that mechanical system what we do today cannot last more than 20-25 years, but same natural materials like stone and the brick and all those things which we use can last for longer. So, durability plays important. Adaptability, they need to get adapted. Now, adaptability plays a very important scenario, because what happens when the building material is gone? Now, whether we can reuse it, whether it can be reused again and again, or whether it needs to be thrown out to landfill. So, it needs to be after the end, it needs to be can be adapted somewhere else. Then also choice of material and construction methods can significantly change the amount of energy. Now, what it means over here is the type of materials you are picking. Always is recommended that you pick materials which are locally available. Reason is the least amount of transportation that is required, so you save a lot of energy in transportation. And also pick up materials which can be recycled or reused, which means that it can be adapted later on. So, choice of material and construction method. In construction methods, use simple construction methods, do not complicate the buildings. Once you start complicating the buildings, the construction method becomes complicated, and that leads to significant. For example, we have simple shuttering layouts or shuttering or centering layouts where you have a specified size. Now, instead of using the specified size, we have something which is out of the box and you have curve. What happens is you need to redo the entire centering and shuttering layout only for that specific project, which means that after that you throw that entire material. What happens to the embodied energy that goes into that making of that centering, and then after that throwing that out. So, it plays a very important. Embodied energy can be equivalent of many years of operational energy. This we will see in a graph in forthcoming forthcoming slides, in a graph that how this happens. This is what it means. Once basically embodied energy initially is huge, as you can see in this graph, the one with a very light blue, the embodied energy initially is huge. It is in gigajoules. The one on the left is in gigajoules. It is not megajoules, it is gigajoules. After certain years of high operating, you will be able to almost meet each other, that is the embodied energy as well as the high operating energy at around 10 years. If you are doing a low operating and the building is a very low operating like a house, high operating is very similar to office spaces where using chillers, equipments, pumps and all those things which get part of it. There you can operational energy would be higher. So, by 10 years you will be able to meet each other, but during the low operating like the houses, it takes almost 20 years to reach the embodied energy that is used in the building. Now, if the building cannot last for 20 years, that means that you have used so much of energy and the building is disintegrating. So, it means as you can see that the longer the building lasts, the embodied energy and the operational energy gap increases. Now, the graph has a small linear upward turn. The reason is you keep on adding certain amount of things, renovating and everything. So, that is the reason the graph is linear. What should be included? Now the question is, initially I have discussed and told you why this is important, what is embodied energy, lifeline, how do we design it, because at the end of the day we are architects and designers, we need to understand how we design. But it is also important that there is a different methods of calculating or understanding embodied energy. When you go online, you will be bombarded with different values of embodied energy. To understand that, you need to understand what is included when you are calculating embodied energy. Energy used to transport the materials and workers to the building site is included. Materials required for footing, structure, walls, basically entire building, what is there is included. The material for construction of the building shell, all materials used to complete such bathroom fitting, driveways and footpath also included. So basically the most important thing that most of us forget is the transportation of the material. Now transportation of the material is could be a huge factor. Now that's where it comes down, that you need to have locally available materials so that you reduce the transportation embodied energy. And also is the upstream energy input, now such as factories. Now steel is made in factories, the factory has lighting, the energy used in making, maintaining the machines to make the materials, so all this gets included as the energy. It is not just the energy that is required to make the material, is also the running cost of the factory, the materials which are part of it, that also is part of the embodied energy. Embodied energy for urban infrastructure is huge. Roads, drains, water, energy supply, all this also is part of the embodied energy. Till now we have seen what embodied energy is, what is included, how it has an impact in terms of the building, if depending on the lifeline. Now there are two terms generally used while measuring embodied energy. One is gross energy requirement, measuring the true and the total embodied energy of the material, which is the most ideal method to use it. The second one is a process energy requirement, is a measure of energy directly related only to the manufacturing of the material, is a very simple quantified amount or figure. Now normally or generally the figures what we find online or in the books are PER. GR, which is gross energy requirement, are very difficult to get it done. Now reason is very important that GR will include everything from the factory to the manufacturing to the transportation to processing to coming back and everything. It is cumbersome to get that values, because not every factory has the same process. They have different processes, they have different methods, there are different places where the extraction happens. So it becomes a very difficult to get a generic idea. For example, what is the what is the embodied energy of a steel? Now this could vary if the steel is manufactured, extracted, everything within a single state like Tamil Nadu, Karnataka or Maharashtra, and it has been used over there. But if the same steel is being transported to China or drawn back, then the value would drastically change based on the embodied energy, because there is huge amount of embodied energy that is required for transportation. That is the reason most of the calculations, for simplicity purpose, we use PER accounts. Now here are few of the tables that I will be illustrating to just to make you understand the different materials, because here we are not going into detail. This exercise or module is not teaching you to do the entire thing and become a masters in embodied energy. This module is basically to give an understanding of the different materials and what are the impacts of embodied energy within our system. Since it is a sustainable design course, it needs to be addressed to that. First, looking at the material, here is PER values. I will be stressing it, it is just the PER values, not the gross, not the complete picture. Aluminium uses quite a lot, it is the topmost compared to the glass. Then you can see steel and everything. So 170 megajoules per kg compared to glass, which is 12.7. So now you will be asking what is megajoules per kg. Just to give you an understanding of it and how this works out, 1 watt, which is the bulb, simple example is a bulb is 40 watt. So 1 watt is equivalent to 1 joule per second. So 1 kilowatt is 1 kilojoules per second. 1 kilowatt hour, which is hour is into seconds, gets converted into 3600 kilojoules. 1 kilowatt is released over 1 hour, which means 1 kilowatt joules per second. 1 minute is so much. So that is how you get the value 3600 kilojoules. Now, if I want make 1 megajoules per kg, then I need to take 1 mega means 1000, so 1000 kilojoules divided by kg is 3600, because it is an hour that we are calculating it, the entire thing. So, converting 1 megajoules per kg into kilowatt hour per kg. The reason why I am doing this is your values, certain values will be in megajoules per kg, PR values, certain will be kilowatt hour per kg. Now, this is where it becomes very difficult to understand which one is right, which one is not wrong. So, that is the reason this tabulation of conversion from megajoules to kg and kilowatt per kg will be very helpful. So, here there is one more, this is again a comparison. Now, previous slide where we saw it, we saw that it was about materials. In this slide we will just talk about embodied energy of the component. Now, component over here is MDF. MDF is not just one single material, there are so many processes which goes into gluing and everything. That has around 11.3 megajoules per kg. Similarly, plywood is little lesser, coming down to cement is much lesser, plasterboard is much lesser. So, if you go down and down, if you look at the least one, a dried sawn hardwood or stabilized mud earth block. Now, most of us when you are designing eco houses or sustainable houses, we prefer stabilized earth block. One of the reasons, one of the best reasons of why we use it is because of this embodied energy. It uses least amount of embodied energy compared to most, like the clay brick or the bricks which we use normally, clean dry bricks or whatever bricks we use. Now, clay bricks and clean bricks are 2.5. When you compare 2.5 embodied energy megajoules per kg to 0.7, it becomes quite a difference in terms of the overall energy of the building. So, to summarize it, now the previous ones what we looked at was megajoules. Now, same thing we are looking at kilowatt per kg. That is the reason that small tabulation was given, so that if it becomes in kilowatt per hour, you should not be worried, oh, it was megajoules per kg, why did it become kilowatt per hour. Now, over here again you can basically see in the summary that aluminum is the highest, then coming down to in situ concrete is lowest, because you are doing the entire process on site. Then in comparison to the material or assembly, so if you have elevated timber floors, if the entire, this is basically the entire floor, the megajoules per meter square would be higher, is lower compared to a concrete one, especially if it is a precast and a concrete slab on ground, it is pretty much on the same line. Roofs, timber roofs initially with the plasterboard without any insulation or anything of concrete for tiles and everything is lesser. Similarly, coming down to assemblies of different walls, if you look at walls like ACC block work or stabilized earth ramp block, stabilized earth is much lesser, which has, even if you include 5% of cement into it, is still much lesser than the normal earth block. Similarly, if you come to cavity brick wall uses huge amount of energy. Cavity brick wall with plasterboard internal filling, like for example, you are filling with plasterboard internal, huge uses, it is almost like double what you are using with stabilized mud block. So, it becomes very important to understand which one you need to use. This tables which have been provided in this module is basically to give an understanding as to how each component of works and how each one has an impact on the total embodied energy of the building. So, if while picking up anything or selecting a material while designing, you need to look at which one and why you are using it, what is it. Embodied energy is not the total picture of the eco houses, it is also important that how you recycle them. So, it is just a basic gist or the first initial step to make sustainable eco house friendly. Similarly, this chart which we have put over here is a very interesting chart. Reason is, aluminium, as we saw in the previous slide, uses huge amount of embodied energy, uses huge amount of embodied energy, but it can be recycled. Almost close to 95% of it could be recycled, which means that since initially we are using huge amount of embodied energy, but at the same time that is not going to the landfill, it can be recycled to 95% and reused, which means that the embodied energy in the extraction of bauxite and other things can be reduced drastically. But when you look at the glass products, okay, with the embodied energy to compare to the savings, there is only hardly 20% of that can be reused. So, though the glass is less in compared to the total PR embodied energy, but it cannot be reused. So, this becomes a very dicey situation as designers, that what to pick and what to leave. So, it is a wise decision, or a clever designers will choose which can be used and reduce the embodied energy, at the same time use things which can be recycled, because at the end of the life of any building, the materials should be recycled. As we spoke about adaptability in the initial stages, this is what it means. This slide, which we always speak about, now the trend is to have solar panels on the rooftop. This was one very interesting one which I wanted to show the architects while looking at this module, that PV uses huge amount of embodied energy comparatively, but now it takes only 2 years to mitigate that. So, what within 2 to 2.5 years, a normal multicrystalline would pay back the entire energy which is used in the generation of PV. There was a myth, or not a myth, it would be the thing that the PV industry was very new, it was in the infant stage. So, this initially would take around 7 or 8 years to pay back the energy that was required for PV generation, for PV panels, but due to the advancement of silicon chips and other things, that payback has reduced drastically to just now 2.5 years, which is significant, because if you are using PV panels, now somebody asks you, oh, so much of energy goes into it, when do you get? This is a very simple answer, that within 2.5 years you get back that. Now, this is basically the guidelines for reducing embodied energy. Now, any designer, anybody who is designing buildings, we have just based on, after going through what is embodied energy, what are the different values, how do you go about it, it is important that we basically understand this, and to complete the entire module, we have put the entire thing in one single thing called guidelines for reducing embodied energy. First one is always design for long life and adaptability, using durable low maintenance materials. Aim to use materials that can easily be separated, which means that if you want to replace something, you can easily separate rather than breaking the entire thing. Avoid building a bigger house than you need. This will save a lot of materials. We have a craze to have the villas, the best villas and things, but do we actually require it? Ask that question before we design it. Always modify and refurbish instead of demolishing or adding a new building. First preference is always modify and refurbish. If it does not, then demolishing would be the last option that you need to look at. Arrange for materials for demolishing of existing material and construction waste to be reused and recycled. As I said, it is important that the materials needs to be recycled and reused somewhere. So, arrange it, do not allow it to be sent to landfill. Use locally sourced material. This is the first and foremost. Whenever you are looking at materials to be designing for new buildings, look at the locally sourced. The reason is it reduces transport, but also it helps the local industry to develop, which means that you are giving employment to the industry. Select low embodied materials, which may include materials with high recycle content. Nowadays, lot of green building councils have started putting this thing, like for cement, they use fly ash as a part of recycled component into it. Steel, they ask certain amount of reinforcement steel has to be, there should be certain amount of recycled content that you need to prove it. So, similarly, there are a lot of other materials which are coming into market. So, like aluminum, they prefer the recycled aluminum to it. So, it is better to select those materials. Avoid wasteful material use. What it means over here is design buildings in such a way that if the plywood is 8 by 4, what you get in the market, design the interiors in such a way that you use that 8 by 4 rather than wasting the material, because at the end of the day that waste is added on to your embodied energy that has been thrown out. Specify standard sizes, that is what I mentioned before, that you specify proper standard size, do not use energy intensive materials as filters, fillers and everything. Arrange for offcuts to be recycled, avoid redundant structures, etc. So, some very energy intensive finishes often have high wastage levels. Select materials that can be reused and recycled, which I have already mentioned it, easily at the end of life using existing recycling. So, we cannot go and what you call manufacture, we cannot go and invent a new recycling system. We need to be smart enough that whatever we have, we use the same system for recycling and reusing it. Give preference to material manufacturers using renewable energy sources. Whenever you pick up any material, please ask them how is this procured. If it is procured from a green source like solar energy, wind, then the factory is using solar, wind, then use them, because they are created using renewable, which also add-ons to your embodied energy, which reduces the embodied energy in the manufacturing process. Use efficient building envelope, as I have explained in the previous one of the previous slides, that how a design A, B and C could make a difference in it. So, basically this is what the entire embodied energy is all about. Okay. So, this assignment, what we need to do about it is simple, we have kept it very simple. So, as we have seen it, that is basically given a gist So, what you need to do is one line, find the embodied energy of the fiber, cement, plywood, plaster or corrugated and softwood in a boring, and please list the problems you could encounter if you wanted to use newly demolished brickwork for a building nearby it. This is very challenging. So, we would like to see what the answers would be for this, because it is quite a challenge that how will you use a newly demolished brickwork from a building. Compare the energy inputs between the installation of in-cast concrete walling and the precast concrete panels. So, this is pretty much the assignment that we would like you to do. Hope this module was useful to understanding what embodied energy and basically giving a intro to what embodied energy is. With this, there will be a subsequent model which will give you understanding of how to calculate it in the next module. Thank you.